Hey there. You know how much I love a good geometry puzzle, and you've mentioned your own interest in the topic. Well, get ready for a deep dive into the granddaddy of all geometry books, Euclid's Elements.
Elements, a classic.
We're going way back in time to explore how this book shaped the way we understand shapes, lines, and spaces.
It's amazing to think that the geometry we often take for granted was born out of very practical needs thousands of years ago.
Right, like I was just reading this source, Introduction to Euclid's Geometry, and it talks about how ancient Egyptians used geometry to redraw property lines after the Nile flooded.
Oh, yeah.
Talk about a real estate nightmare.
Every year the Nile would flood, wiping out those carefully marked boundaries. So the Egyptians had to develop really reliable ways to measure and reestablish those lines, which pushed them to create practical geometric rules for calculating areas.
And they didn't stop there, did they? I mean, figuring out the area of a rectangle, that's one thing. But the Egyptians even knew how to calculate the volume of a truncated pyramid. That's blowing my mind. How did they even start with that?
It's pretty incredible. Imagine trying to figure that out without modern math. They likely used a combination of observation, experimentation, and some surprisingly sophisticated geometric reasoning. And here's the thing. Some of these techniques laid the groundwork for the more formalized geometry that Euclid would later develop.
It's like they were laying the first bricks, so to speak, of this whole system of understanding shapes and spaces. Speaking of bricks, did you know that the Indus Valley civilization was onto something with their city planning?
Absolutely. Places like Harappa and Mohenjo-Daro, these ancient cities, they weren't haphazardly thrown together. They were incredibly well planned, with streets and buildings laid out in a precise grid system.
That's got to take some serious geometrical know-how. Were they using protractors and rulers back then?
Maybe not protractors and rulers as we know them, but they certainly had a grasp of right angles, parallel lines, and standardized measurements. They even used standardized brick ratios in their construction, showing a deep understanding of proportion and geometry.
Okay, so we've got the Egyptians measuring land, the Indus Valley folks building planned cities.
Yeah.
What about other ancient cultures? Was everyone in on this geometry game?
Oh, yeah, and each culture added its own unique flavor to the mix. Take ancient India, for example. They had these ancient texts called the Sulbasutras.
The what is?
Sulbasutras, they were essentially instruction manuals for constructing altars and ceremonial platforms.
Okay, so like blueprints, but for religious structures.
Exactly. And these weren't just your average backyard setups. These altars had to be built with extreme precision because their shape and area were believed to directly impact the effectiveness of religious rituals.
It's amazing how much importance they placed on getting the geometry just right. So we've got a lot of ancient civilizations using geometry in really practical ways. But then something changed, right? It became less about just doing geometry and more about understanding the why behind it.
You're right. It's a pivotal shift, and it takes us to ancient Greece, a hotbed of intellectual curiosity. Thinkers like Thales, who lived around the 6th century BCE, weren't satisfied with just knowing how to do something. They wanted to prove why it worked.
So instead of just accepting that a circle is divided in half by its diameter, someone like Thales wanted to prove it without a doubt.
Precisely. And that's a big deal. That pursuit of proof, that's a cornerstone of how we do math and science today. Thales is credited with the first known mathematical proof showing that a circle's diameter always bisects it.
That might seem obvious now, but back then it was groundbreaking. And that focus on logic and proof set the stage for even bigger names like Pythagoras, whose theorem you might remember from school. So we're on the brink of Euclid's Elements, this game-changing book, but before we crack it open, it feels like we need to set the scene. What was different about Euclid's approach that made his work stand out from everything that came before?
That's a great question. Imagine building a house. You wouldn't just start slapping on walls and a roof without a solid foundation, right?
Okay, I see where you're going with this.
Exactly. Euclid was like the master architect of geometry. He said, hold on, before we go building elaborate proofs and theorems, let's make sure we're all working from the same blueprint. And that blueprint, my friend, is elements.
So he provided that solid foundation for geometry that was missing before. Tell me more about this blueprint. What's in it?
Euclid starts by defining the basic building blocks of geometry: points, lines, planes. He wants to make sure everyone is on the same page about what these terms actually mean.
That makes sense. But isn't a point just a dot and a line as, a line? It seems kind of self-explanatory.
You'd think so, right? But Euclid takes a very rigorous approach. He realized that some terms are so fundamental that trying to define them can actually lead down a rabbit hole.
Oh, I see. It's like trying to explain what the color blue looks like to someone who's been blind since birth.
Exactly. Some things are just better understood intuitively. From these basic undefined terms, Euclid builds up to definitions of more complex shapes and figures. But the real brilliance comes next with his introduction of axioms and postulates.
Okay, here we go. This is where it gets all mathy, right? Axioms, postulates, those sound like words I used to highlight in my notes and then promptly forget.
Don't worry, they're not that scary. Think of axioms as universal truths that we all accept without question. Things like, things which are equal to the same thing are also equal to one another.
Okay, yeah, that makes sense. It's like saying, if my shoe size is the same as yours, we wear the same size.
Precisely. Axioms are the bedrock principles that apply not just to geometry, but to logic and reasoning in general. Now, postulates are a bit different. These are specific to geometry.
So axioms are like the universal laws of logic, and postulates are the rules of the geometry game.
You got it. For example, one of Euclid's postulates states that a straight line segment can be drawn joining any 2 points.
Okay, that seems pretty straightforward. Connect the dots.
Right. But from these simple, intuitive postulates, Euclid builds up his entire system of geometry.
That's amazing. So all those complex geometric proofs and theorems we vaguely remember from school, they all stem from these basic axioms and postulates.
It's incredible, isn't it? But here's where things get really interesting. Among these postulates, there's one that caused quite a stir throughout history, Euclid's fifth postulate.
Ah, yes, the infamous fifth postulate. Why was that one so controversial? It must have been a real head-scratcher.
It was. It's more complex than the others, dealing with the idea of parallel lines. Essentially, it says that if you have a line and a point not on that line, there's only one other line that can be drawn through that point that will be parallel to the first line.
Okay, I vaguely remember learning about parallel lines, those lines that never meet, right? So why was this specific postulate such a big deal?
Well, for centuries, mathematicians felt like Euclid's fifth postulate wasn't really a postulate, but rather a theorem in disguise. They were convinced they could prove it using only the other four postulates and the axioms. It seemed so obvious, so fundamental, that they thought it had to be a consequence of those simpler rules.
So it was like the missing link that mathematicians were determined to uncover. I'm sensing a plot twist coming.
And you'd be right. What's fascinating here is that their struggle to prove the fifth postulate, their utter failure to do so, ended up leading to a revolution in mathematics.
So they just kept hitting that brick wall trying to prove it.
Yeah, for centuries they were convinced they could find the answer, but it just never quite worked out the way they expected.
And it's that failure that opened up this whole new realm of geometry.
It's pretty mind-blowing when you think about it. Their inability to prove Euclid's fifth postulate, it's what led to the discovery of these non-Euclidean geometries. Like, imagine thinking, the absolute rules of the game, and then boom, the game changes entirely.
So what are these non-Euclidean geometries? Are we talking about like circles becoming squares or something?
Not quite. It's more about how space itself is perceived. In Euclidean geometry, the one we're most familiar with, you have these assumptions like parallel lines never meet and the angles of a triangle always add up to 180 degrees.
Right, those classic geometry rules.
Exactly. But in non-Euclidean geometries, those rules, they don't always apply. Think about it this way. Imagine drawing a triangle on a flat sheet of paper. Those angles will always add up to 180 degrees, but now try drawing a triangle on a sphere like a globe.
Okay, I can picture that. What happens to the angle?
They're going to be bigger than 180 degrees. Because the surface is curved, the lines of the triangle are curved too, which messes with our usual angle measurements. That's spherical geometry in action.
Okay, my head's spinning a bit, but I think I'm starting to get it.
Yeah.
So Euclid's geometry, it works fine on flat surfaces, but as soon as you introduce curves, like on a sphere or in the vastness of space, you need these non-Euclidean geometries to make sense of things.
Exactly. And these non-Euclidean geometries, they're not just theoretical concepts. They have real-world applications.
Oh yeah, like what?
We'll take Einstein's theory of general relativity, for example. It describes gravity as a curvature in space-time, a concept that wouldn't even be conceivable without non-Euclidean geometry.
Wow, so we're talking about stuff that's fundamental to our understanding of the universe?
Absolutely. It just goes to show that Euclid's Elements, while groundbreaking, it wasn't the final word on geometry. It's incredible to think that for centuries, mathematicians tried to prove Euclid's fifth postulate, and their failure to do so, that's what opened up these incredible new avenues of mathematical exploration.
It really makes you appreciate those failures, doesn't it? They might not give us the answers we expect, but they can lead us to something even more amazing.
Couldn't have said it better myself. It makes you wonder, if we ever encounter an alien civilization, would their understanding of geometry be based on Euclid's axioms, or would they have developed something totally different based on their own experiences of space and shape?
And that's a question to ponder. It really highlights how much our understanding of the world is shaped by our own perspective.
It does, and who knows, maybe out there in the vastness of the universe, there's an alien civilization grappling with their own version of Euclid's fifth postulate.
That's a wrap on this deep dive into the world of Euclid geometry and the mind-bending possibilities of non-Euclidean geometries. It's been quite a journey.
It certainly has.
Thanks for joining us.